Hello, everyone. Today it's discussion 12, and we're really talking about two things: logistic regression and backpropagation in neural networks. But just to start off with, I wanted to say a little about the chain rule, because the chain rule is pretty important for both of these. So what is the chain rule? Suppose you have some like y. So y is some value, and it depends on x, right? And in particular, the way y depends on x is that y depends on some function, let's say f, and f depends on x, but that's the only way that y depends on x, right? And what we want to know is we want to know dy on dx. If you change x a little bit, how is that going to change y? And what the chain rule tells us is that dy on dx is equal to dy on df times df dx. So df dx, right? If you changed f a little bit, if you changed x a little bit, how would f change? And then dy df, if you changed f of x, if you changed this whole thing a little bit, how would y change? So it's pretty simple, right? You can almost, there's a suggestive proof where you just cancel out the dfs. That's not how mathematics works, unfortunately, but it almost is. So it seems pretty simple in some sense. If it doesn't seem simple, that's okay. Maybe it shouldn't seem simple, but it might look simple. But importantly, we're going to get a lot of juice out of this chain rule. So I just want to kind of explicitly kind of say it up front. And I guess the intuitive proof is like you wiggle x a little bit, what happens to y? Well, the answer, I mean, the way you figure that out is you wiggle x a little bit, then what happens to f? And then, okay, you've wiggled f, what happens to y? And those are the two things you should need to know, and you should need to multiply them, right? Because like dy df is if you wiggle f 1 unit, how much does y change? But df dx is if you wiggle x 1 unit, f might wiggle a few units, and then so you have to multiply that by, okay, if you wiggled f 1 unit, what would happen to y? So that's my explanation of the chain rule. It might not be very good, but hopefully there are other instructors and you can look it up. And I just wanted to say, to kind of so this chain rule, I want to explicitly write down one other version of the chain rule, or one other, I guess, another situation in which you could use the chain rule. So now suppose you have y, and it equals f1 of g1 of x plus f2 of g2 of x, right? So it's sort of like the situation above where there's a function of a function, but now we're adding two of them, right? So now what's dy dx? Well, what it is it's df1 dg1 times dg1 dx plus df2 dg2 times dg2 dx, right? And that kind of makes sense, because you just calculate the two individual things and then you add them up. But the way that kind of looks is like is it sort of like where x can affect y by two paths, and sort of adding over the multiple paths, if that makes any sense. One way this could come up is if you have a neural network, right? Suppose you have a neural network like this, right? These, there are weights like this, there are weights like this. Suppose this is the output, right? Y. And this is W1, W2, W3, W4, W5, W6, and let's say this one is W7. W7's right here. Well, what's dy dw7? This is getting into backprop a little bit, but the answer is I've mixed everything up, but hopefully you'll forgive me. Well, what's dy dw7? Well, how does y depend on w7? Well, you have this value, like the value of this node, right? Let's call that x1. Let's call the value of this node x2 and the value of this node x3. So y depends on the value of x2, right? And also the value of x3. And the values of x2 and x3, they sort of depend on w7, right? Because w7 influences what x1 is, and x1 here, by this way, it influences what x2 is, and by this way, it influences what x3 is. So it kind of ends up being the case that it's dy on dx2 on dw7 plus dy dx3 dw7, and then these terms you can kind of expand them out, but we're sort of like summing over like how did w7 get to y? There were sort of two paths, right? It sort of kind of affected y this way, and it kind of affected y this way, and so you end up using something like the chain rule. But this version where you've got the plus sign. Okay. So hopefully that wasn't ultra confusing, and maybe it'll become more confused. Maybe it'll make more sense when I actually explain, or when I give you a sense of what backpropagation is. I don't know if I'll manage to explain it. All right, that's the chain rule done. Let's delete all of this for now. All right, now we're going to talk about logistic regression. So logistic regression is you have some feature vector. So let's call it like x1, x2, xn, right? And this is your data, right? Your data is like one data point is like one of these vectors of length n. Another is a different vector of length n. So we're just going to call one of them x1 through xn, and we want to output. We have a label, right? It can be let's say 1 or 0, right? So you've got some data and you want to say like, okay, what's the probability? Maybe the data is like, you've got a bunch of houses, some of which are in the US and some of which are in the UK. And you know things like how many people live in the house, right? That's x1. How much did the house sell for? How much area is in the house? How many bathrooms does it have? And you want to figure out, okay, let's say we'll label it 1 if it's from the USA and 0 if it's from the UK. Okay, what's the, if we just know kind of the details, the object level, the sort of like mundane facts about a house, can we predict whether it's from the US or the UK? So how do we do that? Well, we use this function called the sigmoid function, which is called S in the notes. So S of some input, let's call it T. S of T is 1 divided by 1 plus E to the power of minus T, right? So what's going on with this function? Well, it kind of looks like this. When T is negative, right? Well, like suppose T is really, here's T and here's what S is going to be. Suppose T is like -10, right? So e to the negative T, so e to the negative 10 is e to the 10, which is a big number, right? Mathematically speaking. So S of -10 is 1 on 1 plus a big number which is really, so 1 divided by a big number plus 1 is 1 divided by like a slightly bigger number, which is going to be really small. It's going to be like here, right? This is going to be like s of minus 10. If we look at s of minus 1, right? Then we're looking at e to the minus t is e to the minus minus 1, which is e to the 1. And e is about, it's like very approximately 3. It's about 3, right? So s of minus 1 is 1 divided by 1 plus 3, which is 1/4, right? So here's 1/2, and here's 1/4. So s is going up to 1/4 once you hit minus 1, right? Now, what about s of 0, right? Well, then what's what if t is 0? Well, if t is 0, then e to the minus t is just 1. So s of t is 1 over 1 plus 1. So it's exactly 1/2. What about when it's 1? Well, then e to the minus 1 is 1/3. So s of 1 is 1 on 1 plus 1/3. So if you multiply top and bottom by 3, that's 3 divided by 3 plus 1. So that's 3/4. And then when t is 10, e to the 10 is really big. So s of 10 is 1 on 1 plus, sorry, e, now we're talking about e to the minus 10, right? E to the minus 10 is a really small number, right? So this is approximately 1 divided by 1. So it's about 1, right? So basically, what this logistic function, this sigmoid function, what this s does is it takes an input t, and if t is big, it outputs a number really close to 1, and if t is small, it outputs a number really close to 0. So the way we're going to use s of t is, first we're going to say, okay, my input data x, first I'm going to have some weights, right? I'm going to take weights dot with x, right? Now what I'm going to do is I'm going to try and pick the weights so that if the weights dotted with x is like really big, then it's really likely to be 1. And if it's really small, then it's really likely, if it's like really negative, then it's really likely to be 0. And how do I cache that out? Well, what I say probability that y equals 1 given the data x and the weights w is my logistic function or my sigmoid function of w dot x. So that's equal to 1 divided by 1 plus e to the minus weights dotted with x. So that's logistic regression. We're trying to find some weights so that our classifier is outputting like a probability that this like vector of data points represents a 1 or a 0. And how do we train logistic regression, right? How do we find the ideal weights? Well, what we do is we use gradient descent. We have some loss function. We say like, okay, the probabilities, like for our training data, we want the probabilities to be really close to the actual label, right? If the label is 1, we want this probability to be really close to 1. And for this probability right here, and if the label is 0, we want the probability that the label is 1 to be basically 0 because it's not 0, right? Then what we do is we find the derivative of some loss function with respect to each like wi, right? Each w is this big weight vector, right? w1, w2, all the way to wn. We find the derivative of the loss with respect to each w, right? And then we change w a little bit by subtracting off a multiple of the derivative. And what that does is that changes the loss to be like kind of smaller. So that's stochastic gradient descent. It's stochastic because we're kind of looking at like one single data point that we randomly chose rather than like all of the data we possibly could. And it's gradient descent because we're sort of using the gradient to descend down the loss curve. We're moving to values of the W's that have lower loss. So that's why we're descending, if that makes sense. Again, we'll explain this in more detail. I hope this isn't just needlessly confusing. But that's what we do. And I just want to say one final thing about logistic regression. And the thing about logistic regression is, so d loss on dwi, right? Well, loss is going to be a function of like what the probability was, right? So it's a function of this s, right? So this is going to be equal to d loss on ds times ds on d, w dot with x times dw dot with x on d wi, right? So d loss ds is going to be where you can define your loss function. So this should be easy. And dw dot x dwi, that's xi, right? Because it's xi times wi plus a bunch of things that don't involve wi. So what's ds dw dot x, right? That's if that were simple, then it would be like really easy to do stochastic gradient descent for logistic regression. Well, that's just, I mean, the value of that is just like s prime of t, right? Where t is w dot x, right? It's ds dt. Now what's that? So we can actually work this out, right? So it's 1, so we're doing d on dt of 1 plus e to the minus t to the minus 1, right? So firstly, we do the derivative of the outside. Again, we're using the chain rule. So derivative of the outside is negative 1 plus e to the minus t to the power minus 2. Then derivative of the inside with respect to t. So we've got e to the minus t. So you differentiate that, and you have minus e to the minus t, right? Cancel out these minus signs. And that's equal to, and I'll write it out suggestively. That's 1 on 1 plus e to the minus t times e to the minus t divided by 1 plus e to the minus t. And to write it even more suggestively, that's 1 on 1 plus e to the minus t times 1 minus 1 on 1 plus e to the minus t, right? Because that 1 is 1 plus e to the minus t on 1 plus e to the minus t. Then you subtract 1, and you just get e to the minus t on the top of the fraction. And what that's equal to is that's s of t, 1 minus s of t. So the nice thing about this derivative is once you've computed your value of s, you know the derivative. It's just s times 1 minus s. So that's the really nice thing about this sigmoid, this logistic function, whatever you want to call it. It's very convenient. It means that we don't, this calculation, we only had to do it once. We never have to do that math again. So that's nice about logistic regression. And if that didn't make that much sense, hopefully it'll be explained more when we actually do a problem. So finally, what's the deal with backpropagation? Well, let me just clear all this stuff away. So backpropagation, you have a neural network, right? And you want to find, it has a bunch of parameters, right? It has a bunch of like weights, right? And you put in a data point, right? And you get an output. So say your data point is X, your output is Y, and Y sort of depends on W as well as X, right? And well, let's say you get f of X, right? F is your neural network function, and X actually has something as Y, right? X is like the data, and Y is the true label. And you want f of X and Y to be close, right? These things should be close. And the way you do that is gradient descent. Again, these W's, you adjust them. You have some loss of X and Y, right? And what you do is you find like D loss, dW, and you use D loss dW to change W using the gradient descent algorithm. Okay, so how do you find this derivative, right? Like if you didn't know better, well, like in general, if you have like this confusing function, you want to find the derivative, well, like mathematically. It might involve a lot of calculation, right? It might involve a lot of, it might involve like just trying out, okay, if I like, what if I moved my weights, you know, what if I added this thing to my weights? Does that make it bigger or smaller? If I subtract it, does that make it bigger or smaller? Okay, that tells you something about the gradient. It could be really hard to calculate this, but backpropagation gives you an easy way to calculate it, given that you've already calculated this f of x. So you have your neural network, right? This is my neural network. Okay. So first, so this is the output, which we'll call, I guess y is already used, so we'll call the output z, right? Now, let's call these, you know, W11, W12, W21, W22. Let's give that a 1 off the top, right? And these are the W2, W211, W212, W221, W222, and I'm calling it 1, because it's going from node 1 to node 1. This W212 is going from node 1 to node 2. W222 is going from node 2 to node 2. And then like W31, W3, W32. So what we do is in the forward pass, we have this, you know, X1, X2, X3, X4, X5, X6, right? We have all of these values. So now when we want to calculate the derivative, okay, we get like dz on dw31, say, right? That's not too hard. And then what's dz dw112? Well, that's just equal to dz dx5, which you can compute without too much difficulty, times dx5 dw112. Right, but what's dx5 dw112? Well, x5 right here, the way you get this the value of this neuron, like the activation, what it's equal to is it's some like nonlinearity. So it's like a ReLU of W112 times X3 plus W212 times X4. I guess plus a bias that we haven't really talked about, but let's ignore the biases for now. They just make things difficult. So this dx5 dw112, that's equal to d like that's the derivative of the ReLU. So d ReLU on d I'm gonna call, yeah, d w112 x3 plus w21 to x4. Yeah, d ReLU on d input, right? And remember, ReLU is like, this is what ReLU looks like. So the derivative is either 1 if you're here or 0 if you're here. So this is easy. Times d of this whole expression here, w112 x3 plus w212 x4 d w112 112. Right, so the dx5 dw112, you can see that I've kind of used the chain rule. And this whole expression, this is w112 times x3 plus some other crap. So this is just equal to x3. So because I know all of these, like the values of x3 and x1 and stuff, because I computed them when I did my forward pass. When I'm going, I can kind of do a backward pass where I compute, derivative with respect to this, and then I get derivative with respect to this, and then I get derivative with respect to this, and this, and this. And I guess I don't really need derivative with respect to x1. So that's backpropagation. It's kind of, that was a really bad explanation of the actual algorithm. But hopefully you get the sense that the point of doing it is that you're computing these derivatives and you're doing it step by step. You're doing it step by step, right? Like this is like this thing is something you already computed. And this thing is something you computed in your forward pass. And this thing is either 0 or 1, and it's easy to figure out which one it is. So that's what's going on with backpropagation in a nutshell. I think that was actually pretty hard to explain. So what I'm going to do is I'm going to recommend an online video for you to watch on backpropagation. It's on YouTube, which is a website, probably the website that you're watching this video on right now. It is by somebody called 3 Blue 1 Brown. And the title of the video is, what is backpropagation really doing? What is backpropagation really doing? And hopefully that'll have things make some amount of sense. So that's my basic mini introduction to those concepts. Hopefully, like the combination of that and everything else you've heard makes some degree of sense, but I think it'll make a lot more sense when we actually dive into the problems. So let's do it. First, we're doing logistic regression. It's pretty exciting. So we're classifying data. We have samples. Each sample is one of these feature vectors and a label. And this is, this whole thing is basically what I said earlier, right? You have this logistic function, and you're taking your x's and you're taking the dot product with these weights, wi, and then you're putting that into the logistic function. So what we're going to do is we're going to use stochastic gradient descent. So stochastic gradient descent is for each sample, we're going to find the loss. So how do we do that? Well, the answer is we can just use some math, and it's going to be exciting. So our loss is equal to negative y log h of x plus 1 minus y log 1 minus h of x. So I'm going to call the two things in this sum a and b, right? A is y log h of x, and b is 1 minus y log 1 minus h of x. So now what do? We find dl dwj. So dl, L for loss, dwj, so wj is each one. Well, that's equal to, so L is minus a plus b, right? So derivative log with respect to wj is minus dA dwj. Actually, I'll make it even simpler. It's dl dA times dA dwj plus dl dB times dB dwj, right? And dl dA is just like minus 1, right? So it is minus dA dwj minus dB dwj. Okay, so what is dA dwj? So A is so that's equal to d on dwj y, that's the minus of that, y ln natural log of h of x minus d dwj 1 minus y log 1 minus h of x. Right? Okay, so what's that equal to? So the y's don't depend on the h's. So that's negative y d dwj log h of x minus 1 minus y d dwj log 1 minus h of x, right? And I'll just move this. We don't have that much room, so I'll just move this all up. Yeah, we don't need the a's and b's anymore. Okay, so here's our expression. Now we're going to use the chain rule again. So we've got log of h of x. So this is equal to, so what's d log of h, dh? The answer is 1 over h of x, right? So 1 over h of x, then d dwj h of x minus 1 minus y. Again, what's d log d, what's the derivative of log? The log function, it's 1 divided by the thing that you're taking the log of. So this is 1 divided by 1 minus h of x times derivative of the derivative of 1 minus h of x, which is the same thing, like 1's a constant, so it's the same thing as the derivative of minus h of x. But the minus we can turn into a plus right here. Right, we take this minus sign and just like multiply it by the minus sign in front. So this is just d dwj h of x, right? So now grouping our terms, what we have is 1 minus y on 1 minus h of x minus y on h of x. All this times d dwj h of x, right? So what is h of x? So h of x is just equal to s of w dot x, right? So s of sum over I wi xi, right? And one thing we can do is, well, now we can use the chain rule again, right? So this whole thing here is equal to the derivative of s with respect to its input, right? So it's so that's s of sum over I wi xi times 1 minus s of sum over I wi xi times the derivative with respect to wj of sum over I wi xi, right? Now s of sum over I wi xi, we can make that simpler again by remembering, oh, that's just h of x. That's just exactly what we called h of x. So h of x times 1 minus h of x, h of x times this derivative. So now I'm going to delete this and move it up. So now we've just got to calculate this derivative d on dwj of sum over I wi xi. But this is just xj, right? So it's just xj because only one of these i's is equal to j. So we've got like all these things that aren't wj, and the only term that has wj in it is wj times xj. So this is just equal to xj, right? Okay, so now we don't have to do any more derivatives. We're done doing derivatives. And we remember we use the chain rule a lot. So we use a chain rule. We calculated a ton of derivatives. Can we make things simpler? Well, like maybe, right? Because we've got this h and it's 1 minus h and 1 minus, like maybe we can cancel out these fractions. So what this is equal to is we can cross multiply, right? So h of x minus y h minus y times h of x, right? That's 1 minus y times h of x. And then minus y times 1 minus h of x is y minus y h of x divided by h of x times 1 minus h of x times h of x 1 minus h of x times xj. Okay, so we can cancel this out with this out, and then we've got this minus y times 1 minus h of x. We've got a minus times a minus, so that should be a plus here. Right. So now we've got this minus y h of x plus y h of x. So this all cancels out to h of x minus y times xj. So what does that mean? How could we? So what are we saying? So h of x minus y is the difference between what we predicted and what the reality was, right? So what we're saying is, in what direction could we move wj to make the loss bigger in? Well, it's sort of like, look at the sign of loss, right? Were we too small or were we too big? If y was too small, right, then suppose xj was positive, right? And y was too small. Then if y was too small, then h of x minus y is positive and xj is positive. So what that means is that if we increase w, then we would increase the loss. And does that make sense? Well, yeah, so if we increase w, that increases. Wait, why does this make sense? All right. So suppose, we'll just ignore this, right? Suppose, oh, right, h of x is, yeah, h of x is what we output. So if h of x is too large, right? If h of x is larger than y, right? So what we're saying, in order to increase our loss, right, we would have to make h of x bigger. And the way we make h of x bigger is we make the input bigger. And if xj is positive, then if you make wj more positive, then that makes, the dot product of the w's and the x's bigger. So that makes h of x bigger. So that makes total sense. And you can run through that logic if xj were negative, or if h of x was actually smaller than y. But that is d loss dwj for you. So now what we're going to do is we're going to write down the stochastic gradient descent update for wj, and our step size is eta. Well, what we do is, how do we modify wj? So we're going to replace it. So what we do is we start off with the old value wj, right? We're updating it. So we start off with the old value, and we subtract off eta times the gradient. So the gradient is d loss dwj, but we calculated that, right? That is equal to h of x minus y xj. And the nice thing is that when we're actually doing this algorithm, we know h of x because we just do a forward cross. We know y, we know xj, so we don't actually have to do any tricky algebra computing derivatives or anything. This is just this right here is what the derivative is. So you might ask, why do we subtract off the derivative? Well, the derivative, like dy dx, what it's saying is dy dx is saying it's saying if you increased x a little bit, how much would y go up, right? So d loss dw says if you increased w a little bit, how much would the loss go up? So if that's large, right, then increasing w would increase the loss a lot. So if we decrease w, that would decrease the loss a lot, right? So we want to subtract d loss dw because we want the loss to go down. Yeah, so maybe to draw a picture, right? Suppose like this is wj, and this is the loss, right? And we're right here. Then d loss dwj would be positive, right? And we want to go that way, so we want to subtract a little bit. And kind of the higher, like the steeper the slope, right, the more we need to move in order to get closer to this minimum here. So that's why the amount we move is we're subtracting off the gradient, so we're going in the opposite direction, and it's proportional to the size of this derivative. So that is the stochastic gradient descent update for wj. I'm going to get rid of this because it's sort of going into the next page. Now we're going to do backpropagation. Backpropagation. This is where the magic happens with deep learning. So first of all, we're going to do forward propagation. Didn't see that coming, did you? Doesn't look like backpropagation, but it's the first pass. It's the first part of backpropagation. So we're starting with x equals 1, and we're going to fill in the values of the table. So yeah, so in this node you multiply 1 by 2. So what's 1 by 2? It's 2. I'm a really good mathematician, and that's what you put in I. 1 by 3 is 3, so you put that in II, and 1 by 4 is 4, right? Now, so in part 4, you're taking the sum of this thing and this thing. So so this thing, this node has the value of 2. This node has the value of 3. So 2 plus 3 is 5. So that's my answer for part 4. For part 5, I'm taking the max of this and this. So this is 2. This is 4. So the max of 2 and 4 is equal to 4. And the min, now I'm taking the min of this, which is 3, and this, which is 4. And the min of 3 and 4 is equal to 3. Now, part 5, 6, 7. So here, I'm taking the max of 5, 4, and 3. And the biggest number out of all those is 5. All right, so that was forward propagation. Hopefully it made sense to you. This is not really a normal neural network. You normally don't have that many maxes. You do have some maxes. So yeah, one day, you probably shouldn't look it up right now, but one day you'll learn about max pooling. And of course, the Rayleigh function, which you're very familiar with, has a max in it. So anyway, that's just a simple example of forward propagation. Now we're going to do back propagation. So we have this neural network, weights A, B, C, D, E, F, right? Let me rub out those dots. All right, and we've got these inputs. So first, we've got this ReLU. So R1 is the ReLU of CX1 plus EX2, and R2 is the ReLU of DX1 plus FX2, right? So we're taking these like linear combinations of X1 and X2, and we're doing ReLU. And then these sigmoids, right? They're A times, like it's the sigmoid of A times R1, and this is the sigmoid of B times R2. So sigmoid, also called the logistic function. Maybe I should say, you might be wondering, why am I calling it sigmoid? So sigmoid means like a sigma. Well, sigma is just the Greek letter, is the Greek way of saying S. And you remember the function looked like this. And if you take that curve and you like rotate it around, hang on. Let me, yeah, so you rotate it around, right? kind of looks like an S, right? Well, that's why we call it a sigmoid. That's why I call it a sigmoid anyway. Anyway, so that's what the S's do. The output layer is just the sum of S1 and S2. So we have these weights. And we're running this on like one particular input. X1 is 1 and X2 is -1. And you know what? I'll write in black the feed forward values, and I'll write in red the derivative values. Okay, so we have these values for A, B, C, D, E, and F. And forward propagation, R1 is 2, R2 is 0, S1 is 0.9, S2 is 0.5, and Y is 1.4. Okay, so now using these values from forward propagation, we want to use backpropagation to numerically calculate the following partial derivatives. Write your answers as a single number. You do not need a calculator. Use scratch paper if needed, and we are going to need some scratch paper. All right. So what are we going to do? So first we'll do dy dA, right? So what's dy dA? Well, y is S1 plus S2, right? So really this is dy ds1 times ds1 dA plus dy ds2 times ds2 dA. But S2 doesn't depend on A, right? So this second term is just 0, so we can ignore it. All right. So dy ds1. So y is S1 plus S2, right? We see that here. So dy ds1 is 1. Now what's ds1 dA? So this is d dA S1, which is the logistic function. So I'm going to call that S at the risk of a little bit of confusion, of A times R1, right? So now I can use the fact that the derivative of the logistic function is just equal to the, S of that times 1 minus S. So this is S of A dot products, or multiplied by R1 times 1 minus S of A times R1, and multiplied by d on dA A times R1, right? Well, but now S of A times R1, that's just S1. And 1 minus that is 1 minus S1. And what's d on dA A times R1? Well, it's just equal to R1, right? So S1 is 0.9. 1 minus S1 is 0.1. And R1, we looked it up here, that's equal to 2. All right, so what is 0.9 times 0.1 times 2? I'm bad at doing math in my head, but I can see, I'm looking at some answers, and the answer is 0.18. That's what it's equal to. Okay, so that's dy dA. Now, I'm going to delete this calculation. Now let's do dy dB. So dy dB. So that is equal to dy ds2, which is just equal to 1, right? Times ds2 dB. So I'm just going to cut to the chase and say it's ds2 dB. So that is ds2 d. So S2 is the sigmoid of B times R2. So ds2 d, the input to the sigmoid times d b R2 d dB. So what's ds2 dB times R2? Well, again, that's S2 1 minus S2, because B times R2 is the input to S2. So this is, just saying what's the derivative of this logistic or this sigmoid function. That's dB times R2 times dB is equal to B. Nope, no, it's not. It's equal to R2. Right, so S2 is half. So it's a half times times R2, and that's equal to 0. So it's equal to exactly 0. All right, that wasn't too hard. Okay, so we've written dy dp. Now it's time for dy dc. So what's dy dc? How are we going to compute that? Well, dy dc, how does c ever influence y? Well, it goes this way. So y is a function of S1, which is a function of R1, which is a function of C. So it's dy ds1 times ds1 dr1 times dr1 dc. So really, and remember this this product is dy dr1, right? So really, when you're normally computing backpropagation, you want to have these values like dy ds1, dy dr1. You want to have them in handy, right? So actually, I'm going to go back, and I'm going to go back to computing dy dA, but I'm going to be more deliberate about remembering what the value of dy ds1 is, right? And then I'm going to write it down so that we don't forget. So dy dA, well, that was equal to dy ds1 times ds1 dA. Okay, dy ds1, well, y is s1 plus s2. So that was 1 times ds1 dA, right? And then we did all sorts of stuff to calculate that to get 0.18. But this is what I want to remember. dy ds1 is 1. So let's write that down here. This is 1. All right. Back to the present. We're calculating dy dc. It's a new era, right? So we're computing dy dr1, right? So dy dr1 is dy times dy ds1, which is 1, times ds1 dr1. So what's ds1 dr1? Well, remember s1 is it's the sigmoid function, or which we write as s of r1 times a, right? So what that's equal to is, what's s1? 1 minus s1 times dr1 r1 times a. And yeah, remember we're using this fact a lot. So S1 is 0.9, so this is 0.9 times 0.1, which is equal to 0.09. So 0.09. And ddr1, r1a, well, that's equal to just a, right? And a itself, we can look up in the problem. A is equal to 1. So a equals 1. So 0.09 times 1 is 0.09. So dy dr1 is 0.09, and I'm going to write that down here so that I don't forget. 0.09. All right. So now we can get back to the well, let's remember. Let's delete a bunch of this stuff. So yeah, delete this. So dy dr1 is equal to 0.09. Take this, move it across here. Okay, so what that means is that dy dc is 0.09 times dr1 dc. So what's dr1 dc, right? So r1 is a ReLU of cx1 plus ex2, right? And R1 has a value of 2, right? So what that means is that, so here's R1, and here is CX1 plus DX2. It's this kind of graph, right? So this is, so our derivative is, well, we've got the 0.09 term, and then what it is it's dr1 on d cx1 plus dx2 times d cx1 plus dx2 dc, right? Well, dcx1 plus dx2 dc, well, that's just x1, right? Your x1 is what multiplies c. So it's just this multiplied by x1. So dr1 on dcx1 plus dx2. Well, because r1 is 2, right? We can tell that we're on this side of the ReLU, right? So cx1 plus dx2 must be equal to 2. But on this side of the ReLU, the slope equals 1. So the derivative of r1 with respect to this weighted sum is equal to 1. So it's 0.09 times 1 times x1. What's x1? It's 1, right? That's where our input was. All right. So this thing is also 1. So this equals to 0.09. That's dy dc. All right. So that was a little bit of a, okay, we're still going to face some trouble. All right, but dy de and dy df is going to be easier because I did all of this faffing around, I promise. All right, so I'll get rid of these calculations again. Now it's time for dy dd. So first we want to know what dy ds2 is. Well, that's 1 because y is s1 plus s2, so the derivative is 1. So now it's dy dr2, and then we're going to use that to calculate dy dd. So dy, yeah, all of these are supposed to be partial derivatives. It doesn't really matter. I'm going to continue. Actually, I should probably start using this funny symbol because now d is a variable. So partial y, partial r2, that's equal to partial y, partial s2 times partial s2, partial r2. Right, partial y, partial s2, we know is 1. What's partial s2, partial r2? Well, that's b, right? Or no, it's not. It's s2, 1 minus s2 times b. And why is it that? Well, it's that because derivative of s2 with respect to its input, which is r2 times b, is, just the function value, well, like s2, 1 minus s2, because of this nice property of the sigmoid function. And then derivative of, b times r2 with respect to r2 is b, right? So s2 was 1/2. 1 minus s2 is also 1/2. And b is equal to 1. So it's 1/4. All right. Let's write that down right here. 1/4. That's the derivative of y with respect to r2. Right, why was that convenient? Well, it's convenient because partial y, partial d equals to partial y, partial r2 times partial r2, partial d, which is 1/4 partial r2, partial d. All right, so r2 was dx1 plus fx2, right? But through the ReLU function. So 1/4 partial 1 partial d ReLU of dx1 plus fx2. That's equal to the derivative of ReLU prime, so the derivative at dx1 plus fx2 times the derivative, partial d dx1 plus fx2. But of course, this is just x1, right here. So x1. But now what the question is, what's this derivative with respect to ReLU? Well, if we remember, if this is dx1 plus fx2, this is r2, Yep. The graph looks like this, and R2 is 0, right? So that means we're somewhere in like this branch of the ReLU, and here the derivative is 0. So this whole thing is equal to 0. Okay, not so exciting, but good to know. This whole derivative equal to 0. All right. Next step, what's partial y, partial e? So partial y, partial e. So e is this way, going up here. So what it's equal to is it's equal to partial y, partial r1 times partial r1, partial e, right? What's partial I, partial r1? We calculated it. It's 0.09. Now partial r1, partial e is partial e of ReLU of ex2 plus cx1. And so that derivative is the derivative ReLU at its input, ex2 plus cx1, times derivative of the inside with respect to e, which is just x2. And if you remember the ReLU thing, cx1 plus ex2, it's r2, the value is 2, right? So here the derivative must be 1, right? So this ReLU prime is just 1. And the value of x2 is -1. That's that input. So this partial y, partial e is equal to minus 0.09. And now what's the final part? The final part is partial y, partial f, right? So partial y, partial f, that's equal to partial y, partial r2 times partial r2, partial f. So partial y, partial r2, we can look it up, it's 1/4. And then what's partial r2, partial f? That is equal to derivative of ReLU at its inputs, so dx1 plus fx2 times derivative of this with respect to f, which is just x2. What's the derivative of ReLU at this point? Well, again, we'll draw the picture. R2 is 0, right? So what that means is that we must be somewhere in this half of the ReLU. So but at this half, we're flat. Our derivative is 0. So this whole thing is 1/4 times 0 times x2, so that equals 0. So those are all the derivatives. But I want you to notice that when we did these calculations, it was important that we had access to like the x1 and x2 and r1 and r2, like we used those when we were doing these. And we also used these values here, right? Like these ones you kind of didn't notice we were using. It wasn't so obvious because their values were just 1, but it was useful to have those calculated along the way. Yeah, that's how I always do. If I ever have to do backprop manually, that's how I do it. So that's backpropagation. Hopefully it makes a little bit more sense than it did before. Now that I've kind of done it, now that I've done it explicitly. I hope that was helpful. And I guess I'll do another one of these videos for next week's discussion. So I'll talk to you then. Goodbye.